Okay, so I believe we so this is the second part of this lecture, um, and we stop here and on the system design requirements. I mentioned already. This is very important that you know what are the 6 categories of system requirements. So in the exam, I can ask you to list these 6 categories of system requirements. So they are input-output requirements, technology requirements, performance requirements, cost requirements, trade-off requirements, and system test requirements. And we're going to start discussing each one of them individually. So in terms of input-output requirements, the statement of the problem of design of any system must begin with the definition of the inputs that the system must accept, process, and receive. So this is the information. These are the entities that are going to be interacting with the system. These are the processes that are going to get started the system. So for instance, if you're looking at a project in which you're trying to design this system to transport patients, so in this case, that input is going to be the patient appointment, the patient requirement to get to the hospital. So the input-output requirements for a system to be designed consist of specification of the length of the operational life of the system to be designed. For example, the length of operation phase of the system life cycle, the set of inputs to be accepted by the system to be designed, and the set of input trajectories, which we already mentioned. The input trajectories is, if you're familiar with simulation modeling, if you're representing or you're modeling a manufacturing line, the input trajectory will be those parts that are going to be arriving to this manufacturing line at every time point. Like if you're producing part for an hour, let's say the first part arrives at time 0, the second part arrives at time 5, the third part arrives at time 10. So you know what will be the input trajectory for your line. You know that every 5 minutes a part is going to arrive to the manufacturing line, and you have to process that. So that's what we call an input trajectory. The set of output producible by the system to be designed and the set of output trajectories that are possible. And the output trajectories is the same way that we describe the inputs, we can describe the outputs. So we can say, okay, every starting after 1 hour, every 10 minutes, we're going to get a part out of the manufacturing line. So at time 10, we're going to get an output. At time 20, we're going to get another output. At time 30, we're going to get another output. So we can describe this for our system. The eligibility function that matches outputs and inputs, or input trajectories and eligible output trajectories, that's what we call the eligibility function. And it limits or specifies the behavior of a system to be designed, and is usually based on physical laws. So basically, this is making the connection between the inputs and the outputs. So for the case in which you're designing a system for, again, for transporting patients, the input will be that patient requesting the ride. The output will be taking that patient to the final location. So the link between it, that's what we call the eligibility function. How do you match that input with the output? So every system of interest to systems engineering accepts and processes input and produce outputs. Okay, so here's a list of input examples. These are coming from for computers. So in terms of the computer, keyboard, electrical power, all those could be considered inputs. So every key on the keyboard could be considered an input port for your system in that case. At any given point, the input of the computer will be considered the collective conditions of all the inputs. So in the case of a computer, in the case of most systems, you'll see that there's no just one input coming at every time period. You might have multiple. Like in the case of the computer, you have people clicking on the keyboard, you can have the electrical source, you can have the internet connection, and so on. So if we keep a record over a period of time of all the inputs, that's what we call the input trajectory, as I mentioned already. Output examples. Output from a computer include the monitor image, information on a hard drive, the signals to a model in the printer. Every time that you print something, that's an output. And as we discussed, each pixel of the monitor could be considered an output port of the computer. And at any given time, the output from the computer will be considered, again, all the possible collection of outputs at the given time. Okay, so that's in terms of input-output requirements. Now we want to discuss what we call a functional system design. So the input-output requirement determines a set of system designs that satisfy the input-output requirement. A function system design or functional system design is a system design that satisfies the input-output requirement. So a system that is capable of transforming the input to the output. And could be if a functional system design specifies what the system should do in order to accomplish that mission. So this could be thought as a logical design. Hence, specify what the system should do and not how the system can do it. Okay? Can do what it should do based on the available technology. So at this level, we are not worried about technology. We are just saying, okay, we are going to get this input. We're going to use this process to get the input and convert it into output. Okay, so this is a very important point here. Some functional system design might not be buildable in technology. So again, what we're trying to envision is how can we get the input into the output, but we are not thinking about the technology right away. For example, a functional system design could be defined to specify instantaneous mass transfer, even though we don't have that technology. A function not implementable in technology, known at the present outside science fiction. So at this point, we're saying, okay, input, output, how can we transform this? Oh, let's assume that we have this, or let's think that we can build something like this. But we are not worried about technology right away. We're going to worry about that in the next step, which is the technology requirement. Okay, so the technology requirement for a system to be designed consists of the set of components, hardware, software, human, bioware, considered by the designer and the customer to be available to build the system. The technology for a system to be designed is frequently referred to the available technology or merely the technology. How the system can be built is determined by the existing technology. So again, our system design might be limited by the existing technology, but part of the novelty of the system that you are proposing might have or might need you to come up with something new. Like, again, I always refer back to the example of the hybrid engine. There was a need for a new type of car that provided you with a higher mileage. So typical engines would not were not able to get to that goal. So a new engine was developed that had the versatility of changing between gas and electric power. So even though it is based on existing technology, the creation of that new component, that new technology, make it a new system. Okay, so the technology requirement is how the system can be built is determined by the existing technology. So based on that, we already talked about functional system design. We can transition now, when we take into consideration the technology, into a buildable system design, which specifies how the system can be built to perform as specified by the functional system design, as determined by the technology. A buildable system design is a design specifying the system that results for coupling together components of all which are in the technology. A buildable system design may not satisfy the input-output requirement, That is basically saying that if there's no technology, and this is the best you can do with existing technology, then you might not be able to satisfy that input-output requirement. Like, for instance, if you want to design a car that can fly, then you can say you can do that at the functional system design level, but when you get into the technology, you may not be capable of performing that because there's no technology to achieve that goal. So who has not built system that does not work? Okay, so then we move to what we call performance requirements. The performance requirements specify how well the input-output requirements shall be met in terms of performance figures of merit. So now we are not just worried about meeting the input requirement, but also in terms of how well. Okay, something that we can use as an example, going back to the car, maybe our goal in the input-output requirement is to improve gas mileage. Okay, so, but now in the performance requirement, we want to specify by how much. Okay, so we are going to add some performance figures of merit: expected response time, capacity to respond, and expected quality of the response. For example, performance figures of merit for a car could be acceleration, maximum speed, horsepower, torque, and handling. The performance requirement for a system to be designed is an algorithm by means of which any two functional system design can be compared consistently with respect of how well each satisfies the input-output requirement, and is defined in terms of performance figures of merit and their threshold. So the importance here is when we specify these performance requirements is because at the end we might come up with multiple concepts, and we want to use this performance merit or figures of merit to compare them, to see which one of the concepts is more capable of achieving our input-output requirements. And at the end, we're going to choose that concept that is providing you with the best performance to move forward with our design. Any questions up to this point? Performance requirements. A performance figure of merit is a function defined over the space of the functional system design. For every functional system design, it must be possible to compute or estimate the value of the performance figure of merit. Ultimately, the performance requirement is stated so comprehensively that any two functional system design can be compared with respect to how well each satisfies the input-output requirement, where how well is defined in terms of performance. Performance thresholds for each, this could be like a lower bound if you think about it. Like my car or my new design has to accomplish at least this much. Okay, so for each value of merit, an upper threshold and a lower threshold are defined. In the case of a design of a car, the lower and upper threshold for fuel consumption might be specified as 30 miles per gallon and 40 miles per gallon. A functional system design that has a value for a figure of merit is smaller than the lower threshold for the figure of merit is either impossible or unacceptable. So it would not move forward. Similarly, a system design that has a value for a figure of merit larger than the upper threshold for the figure of merit is either impossible or unacceptable, meaning that you don't want to go that far. And sometimes you think like, well, why don't, if you are capable of achieving a better engine, why companies will not do that? Well, they need to sell cars every year, right? So if they go and put the best car that they can design out there right away, then there might be no need for you to purchase another car for the next 10 years. So they are putting those cars out there and they're pushing the threshold little by little. So every year they can keep their company selling cars. Have you heard about the story of the light bulb? At the beginning, when they were designing the first light bulbs, they can make these light bulbs to last 100 years. So you don't need to replace them. But then they figured out that if that was the case, then they were not able to sell light bulbs. Like everybody was having their light bulb and they would have them for a lifetime. So they're changing the design of the light bulb so they can last for a certain number of days, so people need to buy them more frequently. So that's you can check on that history fact. But yes, that's how you keep your business going. The cost requirements. Cost requirement is based on what the system will cost to build and operate in terms of cost figures of merit. So now we're looking at how much money you have or how many resources you have. It could be in terms of expected capital required, expected operation and maintenance costs, expected life cycle costs, expected environmental and social costs, and trade-off among the cost figures of merit. For every buildable system design, it must be possible to compute or to estimate the values of such cost figures of merit. Okay, so for every possibility of a buildable system design, we should be able to compute the cost for that. Ultimately, the cost requirement is stated comprehensively, so any two buildable system design can be compared with respect to how much it will cost to build and to operate in all dimensions in which this cost must be represented. The cost requirement for a system to be designed consists of an algorithm by which any two buildable system designs can be compared consistently. So we use the cost requirements to compare buildable system designs, and we use the performance requirement to compare, again, also buildable system designs. So we went from functional system design to buildable system design. Now we want to know what is the difference between those and the implementable system design. We say that a buildable system design implements a functional system design when the buildable system design has a mode of behavior that exhibits the same functional capabilities or functionalities as the behavior specified by the functional system design. Remember, the functional system design is based on the input-output requirements. So each of the system functions specified by the functional system design is assigned to execution by one of the more components or subsystems specified by the buildable system design. So from the functions, we have the input-output, we have identified technology that can make that happen. Okay, so we have a buildable system design. Every system exhibits several modes of behavior, at least a failure mode and an operational mode. In addition to this, a computer exhibits the following modes: on-off, internal checking mode when it first turns on, standby mode, safe mode, and others. So an implementable system design, or ISD, consists of a functional system design together with a buildable system design that implements or realizes the functional system design. When a functional system design is realizable by a buildable system design, the pair of design constitute an implementable system design. So if you can make that happen, if you can build a functional system design, then that makes it a buildable and implementable system design. Making sure like the buildable system design is meeting the performance and the cost requirements. So we start with the input-output requirements, right? Then we define the technology requirements, we define the performance requirements. Based on those, we state the buildable system designs, and then if the buildable system design is capable of realizing the functional system design, then we have an implementable system design. The functional system design part of the implementable system design specify what the system is supposed to do in order to satisfy the system requirements. And the buildable system design part specify how it is to be built. So So here's a representation of what we just discussed. So we start with the functional system design. That's what is represented here with the illustration. And then we're going to have multiple options in terms of technology. So that's why we have three boxes here. We have using technology A, using technology B, using technology C. We can come up with three different buildable system designs. So if, for example, if we go back to the car example, this could be an engine, gas engine. This could be hybrid. This could be electric car. So three different technologies achieving the same goal. However, when we look at the implementable system design, there might be two of them that are capable of implementing this with technology. So meeting the requirements or the performance required by the input-output design. So those are implementable system design that we can compare and move forward. If this one is not capable of meeting those, then it is discarded. Okay, so that's and in this case, I think I was using the computer example. So three different technology. This might meet this, so we can move forward. We're going to have an implementable system design for PC and Mac. This one is not implementable, does not meet the functional system design, which was stated here. There's no technology other than these two that will meet that functional system design. Okay, so as I'm showing you here, we have two options in this part. We have the PC and the Mac. But remember, our goal is to move forward with one concept, right? With our system. We're going to choose the best system out of these two to move forward with the realization of the system. So in order to decide which one to move forward with, we're going to use what we call the trade-off requirements. The trade-off requirements, or TR, for a system to be designed consists of an algorithm by means of which any two implementable system design can be compared consistently with respect to trade-off between the performance and the cost requirements. So now we are going to compare them. The trade-off algorithm can only decide the preferences between two implementable system designs. So this algorithm will be compared only two. If you have more than two, then you might need to go and compare two first and then compare the best of the two against the other one. When they are equivalent with respect to both performance and cost, or when the comparison with respect to performance does not agree with the comparison with respect to cost. Two implementable system design can be compared both with respect to performance and cost. Performance because each implementable system design includes a functional system design, and cost because each implementable system design includes a buildable system design. A trade-off figure of merit is a function defined over the set of implementable system designs that is a function that we define with respect to them. The trade-off requirement is usually defined in terms of performance, cost, and trade-off figure of merits and their threshold. So we're going to have this threshold. I'm going to say, okay, we want to meet at least this performance. We want to meet at least this cost. And the performance, a trade-off figure of merit, we're going to have these thresholds, and we're going to see which one meets those the best way possible. Like at this point, we're trying to optimize our chances of being successful. Okay, so we're going to choose the best one out of the two, and we're going to move forward with it. For example, suppose that you have to decide between two system designs, S1 and S2, based on expected revenue and expected cost from each system. So we can let the expected revenues for S1 and S2 be denoted by this function, R of S1 or of S2, and then the corresponding expected cost be noted by C of S1 and C of S2. How can we compare the two system designs, S1 and S2, in terms of both expected revenue and expected cost? Then we can come up with these rules. That's what we call the algorithm. So for example, if the revenue of S1 is greater or equal to the revenue of S2, and if the cost of S1 is less than or equal to the cost of S2, then S1 is at least as good as S2. If the revenue of S1 is greater than, now we don't have the equal sign there, and the cost of S1 is less than the cost of S2, then clearly S1 is the preferred option than S2. Okay, this is straightforward. We're just putting words and operations into this decision-making process. In this case, we were comparing in terms of cost and expected revenue. But you can use other performance measures, like meeting certain requirements in terms of mileage for the car. What if we have this example, like the revenue for S1 is greater or equal to the revenue of S2, but the cost is also greater or equal to. So in both cases, you're good because you're getting a high revenue, but at the same time you're having a higher cost. In this case, we can compute the expected profit and use it as a basis for comparison. So instead of just looking at each performance individually, we can subtract and make the decision based on the profit, which is what is represented here in blue. Another way to perform a comparison is to perform a benefit cost analysis, in which we compute the benefits cost ratio, that is the ratio of the expected benefit to the expected cost. If you remember your engineering economy class, you were supposed to do this type of benefit cost analysis. So basically what you're doing is you're looking at the ratio of dividing the cost, the revenue or the benefit by the cost, and you compare that. This is often referred as the bang for the buck. So we are looking at this ratio, and we can name a B of S1 to be the expected benefit for S1 and B of S2 be the expected benefit for S2. Then if the benefit is greater than S2 or greater or equal and the cost is less than or equal, then clearly S1 is at least as good as S2. Otherwise, we are going to compute the benefit cost ratio, in which we are dividing this again. And if the ratio of 1 is greater than the ratio of 2, then it's clear that S1 is going to be a preferred option. Then we get to the last one, which is system test requirements, STR. The system test situation by comparing candidate implementable system designs with respect to performance, cost, and trade-off requirements. An implementable system design is chosen, and on the basis of the implementable system design, a real system is built. Okay, so we are going to move forward with that concept. The real system must be tested within the concepts determined by the system requirements and the implementable system design. An implementable test requirements is a pair consisting of an implementable system design and a real system built on the basis on the implementable system design. This is very important too. So system test requirements, I can ask you about this in the exam. System test requirements specify for each possible implementable test item the following. First, observance. How the real system shall be observed, sampled, measured, simulated, and so forth in order to estimate a value for each performance, cost, and trade-off figure of merit. The set of estimates of the value of all these figures of merit is called the test data. So we can observe the system in order to know how to measure, how to simulate in order to make sure that we collect the right data, the right information to make a judgment. Conformance. How shall it be proved in terms of test data that the real system is in conformance with the implementable system design from which it was built? Compliance. How it should be proved in terms of test data that the real system is in compliance with the system system requirements. So compliance is looking at we are meeting the requirements. Conformance is looking at that the system is doing what it's supposed to do in terms of implementable system design. acceptance is how shall it be proved in terms of test data that the real system is acceptable to the customer. So these are 4 things that are very important once you have chosen a design to move forward with. We want to make sure that we are specifying the test requirements that we are going to perform to make sure that the design is conforming with the specification and also meeting the customer requirements. A distinction is made here between development testing and system testing. The requirement for the development testing may be different from those for the system testing. So here's an illustration of the system test requirements. So again, we have chosen an implementable system design based on these functional system designs and buildable system designs. Okay, so this is going to move forward and we are going to develop a real system, a new system, right? This is the real system. So we want to prove these 4 in terms of system test requirements. Proof observance, how real the system shall be observed. How are we going to observe this system to make sure that it satisfies the figure of merits. Also, how are we going to prove conformance? How to prove in terms of test data that the real system is in conformance with the implementable system design. We want to prove compliance. How to prove in terms of test data that the real system is in compliance with the system test requirements. And finally, prove acceptance. How to prove in terms of test data that the real system is acceptable to the customer. Any questions? No questions.